Okay, so new recording. And this example I'm going to do is for the last problem that you will see in your section 7.3 homework, the second assignment. And actually, this recording, I plan to use this recording for my other Calculus 2 class as well, okay, when I go over this example. Let me give you a moment to copy this example down, okay? All right, so let me give you like 5 minutes here to copy this example down, and we'll discuss the solution. Okay, so let me talk a little bit about this example. Again, this example is, this will help you do the last question, the last problem in your section 7.3 homework, the second assignment. So, first of all, why is this problem of interest to me? Well, of course, in your assignment where you're You know, you're looking at different applications. You have the mixing problems, and then, you know, you have problems. Let me see here, right? Mixing problems. You have a problem that deals with, uh, sorry, let me just see here. Newton's law of cooling, right? You have a problem like that. And, you know, good, the problems are very much like engineering problems. I wanted to do a problem. I wanted to, you know, I'm trying to include a variety of problems as much as I can. And this problem is a biology problem. So, you know, where are differential equations used? You know, in what fields? They're used in all fields. And you've seen, like, the engineering field and the science field, you've seen examples like with the mixing problems and Newton's law of cooling, you'll see that. But here's a biology application. Okay, so allometric growth in biology refers to relationships between sizes of parts of an organism, skull length and body length, for instance. How many of you notice that uh, like a person that's taller tends to have, for instance, a bigger head? Okay, a bigger, or a taller person. Well, that's a good example. If you look at the skull or the head of a person, like a tall person, do you notice their heads tend to be proportional to their heights? I mean, don't sort of, I mean, I don't know, has anybody ever noticed this? Like maybe with animals, if with animals, you know, if you look at gorillas, the baby gorillas have little heads, little skulls, and the you know, big gorillas have bigger skulls. Okay, it's just make so okay. So thank you, Ange. Yes, and so they're saying that if L1 and L2, or the sizes of two organisms, or the sizes of two organs in an organism at age t. Okay, so organs, you know, you could be talking about, for instance, the heart. Okay, um, then L1 and L2, okay, which are the sizes of these two organs at time t, satisfy what's called an allometric law if their specific growth rates are proportional. And here is the differential equation for this allometric law. Has anybody seen this in a biology course, a differential equation like that? I don't know, is anybody, sometimes we have students that like work at NIH or, you know, and maybe they've seen things like this. All right, well, so what we want to do is we want to solve the differential equation to express L1 as a function of L2. Okay, all right, so again, we have this differential equation. And does it look like in the differential equation that the variables L1 and L2, which are functions of t, does it look like L1 and L2 are already separated? Those variables? Yeah, they're separated. That's right, Ange. So we don't need to really separate the variables. Now, we do have the t variable, but we're going to take care of that. Let's focus on L1 and L2. So on the left-hand side, you have a function of L1, and on the right-hand side of this equation here, you have a function of L2. Let's see how to express L1 as a function of L2. Let's go to the solution. So here we are. Here we are. This is the differential equation. And if you notice, if you were to find the the derivative of the log of L1 with respect to t, By the chain rule, that derivative would equal 1 over L1 times the derivative of L1 with respect to t. That's by the chain rule, because L1 is a function of t. Or you could think of it, well, yes, that's the chain rule. Similarly, on the right-hand side, the derivative of the natural log of L2 with respect to t would equal 1 over L2, because the derivative of the log is 1 over, L2, times the derivative then of L2 with respect to t. So this is just the chain rule. But what they're doing is, in the differential equation, they're putting the results of the chain rule there, and then you got to go backwards to get then the antiderivatives, so to speak. Now what we're going to do is we're going to integrate both sides of this equation here. We're going to integrate both sides with respect to t. I mean, we can do that. This here is an equation. And if you integrate with respect to one side, with respect to t of the equation, you have to integrate with respect to the other side of the equation with respect to t. And this gets us down here. Now, this is very interesting here. What we have is we have the derivative of the log on the left side, the derivative of the log of L1 with respect to t. Okay, so when you take, well, I want to say this the right way. Let me even be more clear here. What you have here, let's focus on the left side, is you have the derivative of the natural log of L1, but then what are you doing? You're taking the integral. Well, what's going to happen then when you take the integral of a derivative? What's going to happen? Like if you had the integral of the derivative of x squared. If you have the derivative of the integral of x squared, that's going to be the integral of 2x dx. And what's that equal to? It equals x squared. You get x squared back. Now, of course, you have, that's right, Ange. Of course, you have a constant of integration, but let's not focus on that. The point is here is that when you take the integral, it's just a little example what I have here, but I hope it'll help you I hope this will help you understand what's going on. When we take the integral of the derivative of x squared, we end up getting the x squared back, and that's the case sort of in general. If we take the integral of a derivative, we'll get the function back, and that's what we did here. That's what we get here. And similarly, on the right-hand side, now, of course, I'm going to have a little constant of integration there. That's fine. And then on the right-hand side, I'll factor the k out, and then same thing. I have here the integral of a derivative. And so the integral and derivative are going to cancel each other out essentially, and that's going to give me the function inside, which is the natural log of L2, plus constant of integration. Now what we have to do is we want to eventually find out what L1 is. So we have a little bit of algebra here. So what I'm going to do is I'm going to distribute the k, that constant k, to both those terms. That'll give me little k, that's a lowercase k. That'll give me little k times the natural log of L2 plus little k times C2, which I'll call C3. So now what I'm going to do is, on the next step, is I'm going to get the natural log of L1 alone. that means I have to subtract the C1 from both sides. So on the right-hand side, I'm going to have then C3 minus C1. Well, I'm going to call that C4. So see how I keep renaming the constants? Well, so let me know if we're good. Let me know if we're good up to this stage. Let's see if there's any questions up to here. Give me a thumbs up if you're feeling comfortable, if you're comfortable so far. Okay, Javier is comfortable, wonderful. All right. All right, well now let's take a look at what's next here. Now, I have k times the natural log of L2. So you have a rule that says if you have the log, natural log, of a to the bth power, that equals b times the natural log of a, right? That's a rule, one of the log rules. So this means then I can put the k as I can write the k times the natural log of L2 as the natural log of L2 to the kth power. And that gets me down to this step. Okay, are there any questions before I go to the next page? Give me a thumbs up if you're feeling good. Give me a thumbs up. I think Ange gave me a thumb up before. Do we have another one? All right, wonderful. Nathaniel, Jinxon, Jan, Taj, excellent, excellent. Okay, so again, we have to find out, and David's good too. Excellent, excellent. All right, we have to find out what L1 equals. Well, this is really just an algebra problem. Going to the next page here. I mean, here's what we had the natural log of L1 equals the natural log of L2 to the kth power plus C4. Now, what are we going to do? We need to get the L1 out of the logs. So we're going to exponentiate both sides. Here it goes. We're doing it again. Exponentiate both sides. And on the right-hand side here, on the right-hand side, this part here, okay, if we remember, again, e to the a plus bth power is equal to e to the eighth power times e to the bth power. So I can write then the right-hand side of this equation as e to the power log, natural log of L2 to the kth power times e to the c4th power. And e to the c4th power, I'm going to call that big K. Now that's a capital K. That's a capital K. And the reason I'm using that is I'm thinking about WebAssign, and I'm thinking about that last problem there in 7.3, that set homework. And I know I'm thinking, okay, in the answer, they want a big K there. So you have little k and big K. All right, well then this equation reduces to this. L1 equals L2 to the little kth power times big K. So therefore, L1 is equal to big K, capital K, times L2 to the kth power is a lowercase k. And that's how you'll write it in WebAssign. Okay, that's how that last one is. Mario, question on that? Okay, Mario's good. Excellent, excellent. So I think this is, there's so many nice applications, so many nice applications of differential equations, and I just wanted to add this one in here for variety. Who here like is interested in biology? Do we have any biologists here, or people that are interested maybe in biology, maybe minoring in it? Or okay, D'Angelo is. Okay, so see, D'Angelo, here you have an app. You can see why calculus 2 is important in biology, right? And so, excellent, excellent. All right, are there any questions before I stop this recording?
Professor,
Yes, Ange.
uh, why we didn't get rid of dt before and then use the integral to find the answer, to find L1 from function of like d
Yeah,
if
let me
dt.
see here. So let me bring up this page. So here we are. Okay.
Yeah, so if like if dt leave, we have dl over d, if dl1 over l1 equal k dl2 over l2, and then when we take the integral of that, he become ln of L1 equal k ln of L2.
Well, I did take the integral. I did take the integral. I was just, I mean, I guess this is just my way of doing it. And I'm not saying my way is the only way, Ange.
No, no, I'm actually I was asking if it is legit to get rid of dt, or if it's not something to do.
Like sort of cross them out here in the
Cross them
first
out
step.
in both, yeah, if it's something we can do or
I,
no.
I'm a little, I'm not, I'm a little uncomfortable with that. I will tell you. I'm very comfortable with what I'm showing you here. But canceling out those DTs, then you'd have differentials. You'd have DL1 and DL2. So, oh, I see what you mean. And then you integrate both sides.
Right.
Ah, I see what you're saying. What you're saying is this. I see what you're saying. You're saying that we could have 1 over L1 DL1 equals K times 1 over L2 sorry, let me write it a little nicer. Hold on. And I know we're going over a few minutes. Let me just, I'm going to be sharing this recording with the other class. So, but what Ange is saying is, why not, take this equation here, that differential equation, and write it as 1 over L1 times DL1 equals 1 over L2 times DL2.
Right.
And
And
then
then
integrate both
integrate that.
sides with integrate both sides. So I'll have to, do it like this. And when you do that, you would end up with I forgot the K. Forgive me. I forgot the K. We know the K's there, right? We know the K's there. But what you would get is you would end up getting this down here. Ange, I'm okay with it. I'm all right with that. Very, very nice. Very nice.
Okay, thank you,
The
Professor.
the textbook I know does it differently than that, but I mean, I offhand don't see an issue with it. Excellent, excellent. Thank you, Ange.
Thank you, Professor.
Okay, all right. Are there any other questions, everybody? Any other questions? Okay, I will stop the recording then.